Welcome to week 5 live session for NPTEL's Introduction to Semiconductor Devices course. I am Om and today we will be discussing some questions that will help you with your assignments as well as your exams. For this week, we will mainly be discussing about the PN junction under applied bias and mainly in forward bias and reverse bias regions. So before going to the questions, let's have a quick overview. So this is an example of a forward bias PN junction where we apply positive bias to the P side and negative bias to the N side. So when we apply the forward bias, so this is the P side, this is the N side, this potential barrier between the P and N side reduces. E VBI minus VA, where VA is the applied forward bias. So this is the minority carrier concentration at the edge of the depletion region, which is basically the minority carriers which are just crossing from N to P side. So electrons here and holes here that have been injected due to this forward bias VA. And the law of junctions is the NP product. Now NP equals to Ni square we have seen is valid only for equilibrium. For non-equilibrium, when we have applied the bias, this is the law. NP equals to Ni square exponential QVA by KT. So the diffusion of minority carrier concentration from edge of the depletion region forward bias. So this is what this is the minority carrier that are here at this edge of the depletion. Now how do it diffuse into the P side is given by this, right? So this is delta NP. This is the first term same as this one, exponential of xp plus x by ln. Xp is your depletion width on the P side, x is your variable, and ln is your minority carrier diffusion length. And the total current is then given as the diffusion. This is the total diffusion current is dn del delta n by del x minus e dp del delta p by del x, which comes out to be this. This is the main equation of the PN junction current that we have seen, diode current. And here this part is your reverse saturation current. So your J total is Js exponential e to power QVA by KT minus 1, which is the equation of current that you already know. And what happens in reverse bias? Let's see. So in reverse bias, you apply a smaller potential to P side and a higher potential to N side, such that this barrier further increases VBI plus VR. And the depletion region, this we have seen last week, this changes in a square proportion of this VR, and the maximum electric field will simply will be VBI plus VR by W. It is total V by W. And the associated capacitance, that is the depletion capacitance, that is the capacitance due to these depletion charges, it's simply epsilon A by D. Here instead of D it will be W. W is the depletion width. So it is capacitance per unit area is epsilon by W, where W is this that we have already calculated. So your Cj is proportional to under root 1 by VR plus VVI. So just a recap from the slides also. When you apply forward bias, the Fermi level shifts downwards and upwards. When we apply a reverse bias, a negative potential is applied. So now we do not have a Fermi level is defined only in equilibrium case. Now, since you have applied a potential, you don't have a Fermi level, you have quasi-Fermi levels, which are like in these quasi-neutral regions, but they are not exactly Fermi levels. Fermi levels only defined in equilibrium condition. So they can tell you the concentration of carriers in this p side and n side. They are not continuous. So the major phenomenon for the current in forward biases that we have already seen is diffusion of majority carriers, right? From here to here, electrons will diffuse. From here to here, holes will diffuse. So basically the electrons from here that are here and the holes that are here, we reduce this barrier by applying a VA that will reduce this barrier so that these electrons can grow from n side to p side and holes can go from p side to n side. That is hole diffusion. Here it is electron diffusion. So diffusion. So this could be a very small drift also. Drift would be the minority holes that are here. Under the influence of this electric field in the depletion region, they sweep on the other side, but that is very small. Since the minority carrier density is small, a drift current can be neglected in forward bias. So this is the carrier profile. This is very important. So we have n side and p side. So from n side, holes, electrons have diffused from n to p side, and here is their concentration. Then they recombine with holes in the p side so that they die out here like this. Similarly, holes have come from p side to n side, and then they recombine with electrons in the n side and diffuse like this. This is the current in the total current in the PN junction in steady state. This we have already seen. This is the reverse saturation current. Okay, so I think that's enough of the recap. I hope you all have seen the videos also. So now let's get to the questions. Question one is the capacitance of PN junction diode A decreases with increase in forward bias, increases exponentially with increase in forward bias, increases linearly with increase in forward bias, and does not change with increase in forward bias. Yes, so option B is correct. It increases exponentially with increase in forward bias. Now in forward bias, as we have seen, P and N, we apply higher potential like this, and across the depletion region, we see there are holes here and electrons here that have come from here, and holes like holes which have come from here and electrons which have come from here. Right, so there is this separated charge. This is this extra holes and extra electrons that are here on the N and P side respectively due to the diffusion. So this generates a diffusion capacitance in forward bias. And diffusion capacitance is given as tau I by eta Vt. Tau is the recombination lifetime. I is your again forward bias current. So this I is actually proportional to e to the power QVA by KT, right? This eta is the ideality factor and Vt is your KT. So this makes it exponentially dependent on this makes the capacitor exponentially dependent on forward bias voltage. So your capacitance in forward bias increases exponentially with increase in the forward bias voltage. Okay, so next let's take another question. If you have any doubts, please feel free to either open your mic and talk, or you can type in the chat if you have any doubt. In the next question, please read it and try to solve it. Okay, so let's see this. The built-in potential of an abrupt PN junction is 0.75 volts. Its junction capacitance Cj at reverse bias is 1.25 volts, is 5 picofarad, and the value of Cj when VR is 7.25 volt is what? So we know that Cj is proportional to 1 by root VBI plus VR. So if you want to find Cj2 by Cj1, it will be under root VBI plus VR1 by the root VBI plus VR2. So Cj2 will be Cj1 VBI plus VR1 by VBI plus VR2. Substitute the values 5 picofarad into under root 1.25 plus 0.25 is 2 and 7.25 plus 1 plus 0.75 is 8. So it is 5 picofarad by 2, which is 2.5 picofarad. CJ2 is 2.5 picofarad. This is option D. Okay, so option D is correct, right? Next question is try this one. All right, so let's see this. Yeah, option C is correct. So this is a very simple question. We have a silicon bar doped with donor impurities Nd. Is this given the intrinsic carrier concentration at 300 Kelvin is 10 to the power 10, 1.5 into 10 to the power 10. We have to find the equilibrium electron and hole concentration. So in equilibrium, we know that Np equals to Ni square, right? So N0 we can assume N0, P0, okay. So N0 can be assumed equal to Nd, which is 2.25 into 10 to the power 15 per centimeter cube. So P0 will be Ni square by Nd, which is 1.5 into 10 to the power 10 whole square by 2.25 into 10 to the power 15, which is 2.25 into 10 to the power 20 upon 2.25 into 10 to the power 15, which is 10 to the power 5 per centimeter cube. So option C is correct. N0 is 2.25 into 10 to the power 15 and P0 is 1 into 10 to the power 5. Okay, let's take the next one. So we have a PN junction is forward bias, and then for the minority CAD distribution, answer the following question based on the graph given below. So based on this graph, we have to answer this question. Yeah. So option B is correct in this case. So we can see it from two things. First is you see the depletion region. Sorry, option A is actually correct. The P side is more heavily doped than N side. B is not correct. A is correct. So one thing is you can see the depletion region on P side is smaller than depletion region on N side, right? And depletion region is more in lightly doped side, which implies N side is lightly doped than P. So one observation can be made from here. Another observation can be made from here also, right? You see this, this is the thermal equilibrium value of Pn0. This is greater than Np0. Right? Pn0 means the minority carriers in N side, the minority carriers in N region in thermal equilibrium. So in equilibrium, if minority carriers are more, that means majority carriers will be less. Compared to here, the minority carriers are less, so majority carriers will be more because in equilibrium Np is Ni square, right? So if Pn0 is higher, this implies N is lower, or Np0 is lower, this implies P is higher, right? So P side is more doped. Is this clear? Okay, sure. So we have two observations to be made here. One is seeing the length of the depletion region on NNP side. Depletion region is wider always on the lightly doped side, right? Depletion region will be higher in the lightly doped side. So here, since depletion region is higher in N compared to P, that means N is less doped, P is more doped. So we can directly say from here that P side is heavily doped. One more observation we can make is you see these thermal equilibrium values of Pn0 and Np0, right? So Pn0, this is the minority in N region. This is the minority in P region. And we know that Np is Ni square, right? So if Pn0 is higher, that will mean N will be lower, right? Because N will be Ni square by Pn0. Similarly, if Np0 is lower, that means P would be higher because N Np0 into P will be equal to Ni square, or P will be equals to Ni square by Np0. And if this is lower, this will be higher. If this, let me write it. P will be equal to Ni square by Np0. So if this is lower, this will be higher. This we can say from the equilibrium concentrations. So again, which again signifies that P side is more heavily doped. Okay, so let's see the next one. So we have to again answer from based on this graph only. Please try to answer this. Okay, so for this one, option B is correct, right? So why N side? Because N side has less majority carriers, therefore more diffusion for more diffusion length for minority carriers before recombination. What this means is, since on this side there are less number of electrons, so when these holes come here, they can travel a much larger distance compared to electrons on this side because there are holes are less. So why do these reduce? They reduce due to recombination, right? So since there are less number of electrons available for recombination, there will be larger diffusion length here. That's why N region will exhibit a larger diffusion length for minority carriers. All right, next question. Okay, so let's see this. The question is, for every 10-degree increase in temperature, the reverse saturation current of a PN junction will be increased by A remains the same, B 10 times, C 2 times, or D 4 times. So option C 2 times is correct. So this is like a well-known fact. And why this happens is uh, your reverse saturation current. What is reverse saturation current? JS is Q Ni square dP upon dLp plus dN upon Na ln. Right? This is your reverse saturation current. So a reverse saturation current is proportional to Ni square, and Ni square is proportional to T cube e to the power minus Eg by kT. Right? So these two temperature dependencies are there, as well as Eg also changes with temperature. But even if we assume, let's say, Eg remains constant for a small change in temperature of 10 degree, then due to this exponential decrease in temperature and then this cubic relation, it comes out to be when JS T1 is okay, or again it is JS T2 is always 2 times JS T1 plus 10. So JS T plus 10 is always 2 times JST. That means for every 10-degree rise, the current doubles. So option C is correct, 2 times. This you can solve also by assuming like T1 and T1 plus 10 here, and then taking the ratio of JS1 and JS2, then you should arrive at a similar conclusion. Okay, so let's take the next one then. Please see this one. All right. So in this question, we have consider the following parameters of PN junction: Na and Nd equal to 10 to the power 16 per centimeter cube. Ni is this. Dp and Dn, the diffusion constant are given, and the Marty array lifetimes tau p and tau n are given, and the epsilon is given. We have to determine the ideal reverse saturation current density in a silicon PN junction at 300 Kelvin. So this, I just wrote this formula about the ideal reverse saturation current is Js is Ni Q Ni square dn upon NaLn plus dp upon NdLp, right? And ln is under root dn tau n, which if you substitute the values, dn is 10 and tau n is 5 into 10 to the power minus 7. So if you solve this, this comes out to be 2.236 into 10 to the power minus 3 centimeter. Similarly, LP is under root dp tau p. So if you substitute the values, which is 25 into 5 into 10 to the power minus 7, LP comes out to be 3.536 into 10 to the power minus 3 centimeter. Okay, now I have these two values. I have this also, this, and NIs also. So I have all the values now. If I substitute now, JS will be equal to 1.6 into 10 to the power minus 19 into NI square is 1.5 into 10 to the power 10 whole square into dn is 10 upon Na is 10 to the power 16 into 2.236 into 10 to the power minus 3 ln plus 25 dp upon Nd is again 10 to the power 16. Lp is 3.536 into 10 to the power minus 3. Okay. So if you solve this, this comes out to be 4.16 into 10 to the power minus 11 ampere per centimeter square, which is option D. Is this clear? Okay. Next question. Okay, so the correct answer is option B. Senior involves tunneling, avalanche involves impact ionization. So I think this is explained in the last video of this week. So what happens in a Zener diode is you have very high doping. So when you have very high doping, you have very thin depletion width. So when you have very thin depletion width, when you apply a reverse bias, what happens is, so this P side, this N side, the minority carriers, electrons tunnel here and holes tunnel here because this depletion width is very thin, so they can directly tunnel. So they explained through their band diagram also. So if this depletion width is very thin, so electrons go from here to here, right? This Zener case, this is tunneling. In avalanche, you have less doping, so your depletion width is considerably large. So when you apply a bias, what happens is, so avalanche happens at a very large bias, very high reverse bias. So the minority carriers, so P, the electron here gets very high energy. It strikes with the ions to generate more electron hole pairs. Generally, hole from here will strike to generate more electron hole pairs. Hole will go this side, electron will go this side. So it involves impacting with an ion. That's why it is impact ionization. Or rather, it is impacting with an atom. Cannot be like ion only. It can impact with any atom of the lattice, could be silicon, and then it ionizes the atom. So option B is correct. Is this clear? Okay, what is the doubt? Do you have a question? Okay, so if there is any doubt in this part, I would suggest please watch the last video of this week's lecture. It's clearly explained by Professor in the video and the differences in the. Otherwise, if you still have any doubts, please feel free to ask me at any point of time. See the next one. Please attempt this question. Okay, so let's see this question. If the depletion capacitance, if the depletion region width of a PN junction increases from 150 nanometer to 300 nanometer due to increase in reverse bias voltage, by what factor does the junction capacitance change? So, right, option B is correct. Cj is epsilon A by W. W is your depletion width. So Cj2 by Cj1 would be W1 by W2. Cj2 will be Cj1 W1 by W2, which is Cj1 150 by 300. So Cj2 is 0.5 times Cj1, right? So option B is correct. Okay, so this is the last question for today. Please try to solve this. So this is an IV characteristics in reverse bias, right? There would be a forward part also, but for now you can ignore it. Be something like this. Currently focus on this reverse part. The question is, in the reverse bias, a change in temperature results in shift in reverse saturation current, Js. Choose the correct temperature relation along with the reason. So what is the JS dependence on Ni and how current changes with temperature that we have to tell. We just saw this question, right? So we saw JS doubles for every 10-degree rise in temperature, right? So one thing for sure is that if temperature increases, your reverse saturation current will increase. So from this, we can say that always TD is greater than TC, right? Or TC is less than TD. This is for sure. Now, second thing is we just saw the formula also, right? JS is Q Ni square dn upon NaLn plus P upon NdLp. So Js is proportional to Ni square. So these two are the conditions that we have to answer in this question. So which of the options has both of these? Not this one. No, in this one, as Js is proportional to Ni square and Tc is less than Td. So this option is correct. Okay. Any doubt in this? Okay. If not, so these are all the questions I had for today. If there are no doubts, we can close the session. So thank you everyone for joining. We'll meet again in the next week. Okay, the question is, can you explain ideal doped? What do you mean by ideal doped? I don't understand, sorry. What is ideal doping? I'm not sure. Okay, non-ideal diode. Okay, so just a minute. So in a non-ideal diode, right? So ideally, we see that um, this is, let's say, an ideal diode characteristics. So it's log I, this is VA, and this is minus I and minus VA. So ideally, current is exponential to, right? I is proportional to exponential of VA by KT. So if I draw log I versus VA, I should get a straight line. But that does not happen usually. So current, how generally behaves is like it is like this till certain day, then it saturates, And here also it has some different slope. So only in this middle region it behaves ideally. Here and here it has some different behavior. So why this is there? There are a couple of reasons for this. So at this in this region, what happens is the slope is not same as this slope, and this is due to the depletion width due to recombination and generation in depletion width. So when forward bias is small, the this recombination and generation in depletion width is dominant. So N and P recombine in depletion region. Due to that, we get this kind of behavior, non-ideality. But after some forward bias, what we assume is a depletion approximation, that there is no depletion or generation in the depletion region. So electron going from here directly goes here. Hole going from here directly goes here. That is the ideal behavior. That only happens after some forward bias is greater than, let's say, 2 or 3 kT, 2 to 3 kT. Then only we get ideal behavior. And what happens in uh, this region, why this current starts to saturate? So this is due to high level injection. So what happens is, in your diode, right? In this diode, we assume there is very less resistance in these regions, right? So, but when your VA is very, very high, when your forward bias is much higher, so in this region, since the current is very high, the IR drop increases, right? So if you are applying, let's say, VA here, effectively at the junction, say VA minus delta is reaching. So your forward bias across the junction is effectively reducing due to the drop in this quasi-neutral regions, which is due to this is called the high level injection case. Due to high level injection, there is much large current here, and this large current causes large IR drop. So due to this, instead of increasing linearly, increasing exponentially, there is some change in the characteristic, and actually it is now quadratic nature. Similarly, the non-ideality in the reverse biases, it does not like remain constant like this. It actually increases after a certain point, that is due to either Zener or avalanche breakdown. So these are the three main non-idealities that that are different from an ideal diode. Okay. Anything else? Okay then. So I will upload the recording as well as the slides, these notes in that Google sheet, and which you can see after the class. If you have any doubts, please feel free to email me. Thank you everyone for joining. We'll meet next week now.